should be good.
All right. Hi, everybody. Thanks for joining us for Dome to Home today. I guess I shouldn't tell you if you're not seeing the stream, you're obviously seeing the stream, but we're going to wait just a couple minutes for some people to refresh their browsers and everybody get set up. Give us just a little minute here. All right. Let's go ahead and get rolling. Hi again, everybody. Thanks for joining us for Dome to Home. My name is Tara. I'm a planetary scientist and a presenter here at Fiske. We also have Parker here. He's our navigator today, our spaceship captain. He'll be kind of flying us around and showing us all kinds of awesome stuff. And everything that you see on the dome over here is going to be done live. Parker's doing all of that. We also have our friend Emily here with us too. She's not on camera, but she's going to be monitoring the chat and helping us keep tabs on any questions that you might submit during the show. So if you have a question or use the chat feature here, let us know. I'll try to answer some as we go, but we'll have some time at the end that's dedicated for questions too. All right, so today and all this week, we are celebrating the 50th anniversary of Earth Day. So today we'll be talking about a common Earth Day theme, the atmosphere. But not just Earth's atmosphere, we're also going to look at the atmospheres of Venus, Mars, and maybe some exoplanets. But let's start at the beginning. I'm sure you know what an atmosphere is, but do you know where atmospheres come from? How do we get an atmosphere to begin with? Well, there's a couple of ways, but one of the main ways that a rocky planet like Earth can form an atmosphere is through a process we call outgassing. It's pretty much just what it sounds like. You're letting gas out from inside the planet. So when planets form, they end up with a lot of gas trapped inside them already. It's gas that gets trapped in the rocks that make up the planet. When that planet comes together, the pressure in the side gets really, really high, melts those rocks, and that gas is able to escape. And some of the gas that escapes, because of the planet's gravity, it'll hang around outside. And some of the primary ways that we can get that gas out is A, through volcanoes, and B, through hydrothermal vents in the bottom of the ocean. So these are things that are still active today. These are processes that are still happening and depositing gases into our atmosphere. Hey, Parker's putting up some really cool, these are the hydrothermal vents at the bottom of the ocean. They're all over the place and they're really, really far down. But those things on the left side, the tube worms there, they get like 6 feet long. They're crazy. They live so far down that there's not any sunlight, and yet they grow to be huge. It's nuts. So the gases that are coming out of the center of the Earth are rich in minerals and all sorts of really, I guess, yummy stuff if you're a tube worm, but really interesting things too. We can also have atmospheric gases that are delivered to us by asteroids and comets. Now, a lot of times they'll have the same kind of gases and ice trapped inside them, just like the other rocks that formed our planet. So that's another way that atmospheres get created at a planet. Most of the asteroids and comets that do hit the Earth aren't very big once they get here. So they're not delivering a ton of gases, but there are a lot of them. In fact, let's take a look at how many asteroids are out there. I think Parker can show us at least the asteroid belt, or what it would look like from here on Earth if we could see it.
Yeah, just give me 1 second here to look.
Yeah. The asteroid belt is out between Earth and Mars, kind of right in the middle. So asteroids usually aren't very big. It's very difficult for us to see them unless they end up really close to the Earth. But there's kind of an idea of what it would look like in our sky if you could see it. There's about 2 million asteroids in the asteroid belt. And even beyond that, there's 2 other huge reservoirs of small asteroid comet-sized bodies. Out at the very edge of the solar system, we have the Kuiper belt, right along outside the edges of Pluto. And then if you go even farther out, there's something called the Oort cloud, which is like a big sphere that encompasses our whole solar system. It extends about 1 trillion miles from the sun, but it's still gravitationally bound to our solar system, which I think is crazy cool. And so there's millions and millions and millions of tiny bodies out there who can deliver these kind of gases and help us make an atmosphere, which is pretty cool. So those are the primary ways that atmospheres are formed, but we know that atmospheres can change over time too. Now that can be because of the same processes or sometimes different ones. And I'm sure you guys know that humans have made a huge impact on our environment, not always for the better. We are releasing greenhouse gases like carbon dioxide at an astonishing rate. In fact, we've got a really cool visual that we can show you of what that looks like if you're outside of the Earth. But to do that, we're going to have to leave the Earth entirely, if that's okay with you guys. Are we good? All right, take us out, Parker.
Yes, ma'am.
We are blasting off here. Here's our big, beautiful Earth coming up beneath us. You can see that bright blue line going all the way around the outside. That's our atmosphere. So you can see how thin it is. It's just a tiny, tiny little envelope of gases surrounding us. So this is a map of the last couple of years of carbon dioxide in our atmosphere. Areas where it's red or where there's a whole lot of it. The blues are where there's not as much. And you can see over time, it starts to get redder and yellower and redder and redder. Not great. Now, Earth's atmosphere naturally does have some CO2 in it. That's what gives rise to plants here on Earth. They breathe that CO2 to create oxygen, which in turn lets oxygen-breathing animals evolve into existence. So it's not all bad. But when you get too much of it, it's such a powerful greenhouse gas, and it sticks around in the atmosphere for a really long time. So once it's created, if it's not breathed in by plants, it'll stay there. And it's able to build up and cause so much damage to the Earth. Earth's atmosphere is in a very delicate balance. So having just the right amount of greenhouse gases is important for regulating temperatures here at Earth and, you know, making it a good place for life to exist. We like that. But of course, it's not just our atmosphere that influences what makes Earth habitable. Our distance from the sun has a lot to do with it too. And I think we can pull out and get a good look at where we are in our solar system. And while we do that, I see that John has a question about why can't we see more asteroids in the night sky if there's so many of them? An excellent question, John. It basically boils down to they're really far away, one, and they're really small. We can't see most of the asteroids just because they're little. Even with really powerful telescopes, it's sometimes really hard for us to see asteroids unless they're really, really big. NASA's state-of-the-art asteroid tracker can track things that are about the size of a football field, but that's the smallest they can get. That's with their state-of-the-art telescopes. So with our eyes, we don't see things until they're either entering our atmosphere and burning up like a shooting star, or, you know, if it's something really, really huge, and if we did see that, that might be actually a problem. But an excellent question. All right, so here is our solar system there. Parker turned on the asteroid belt there for you because you can see how many of those suckers there are. Tons and tons. But like I said, our place in our solar system has a lot to do with habitability too. We have to be at just the right distance from our sun to not get too much heat, but get just enough heat. This is a thing in science, we call this the Goldilocks zone. Every star has one. There's an area, a distance from the star that's just right. I think we had, oh, where'd our picture go? There we go. So the one there on the bottom is our solar system. And you can see that for little Mercury, way too close to the sun, way too hot. When you get farther out into that blue area, those are areas where it's way too cold. But the green, there in the middle, right where Earth is, just right. So not too hot, not too cold. But you can also see that Venus and Mars are kind of on the fringes there. They're not exactly in the Goldilocks zone, but they're pretty close. And so one of the things that actually helps with maybe moving them into a more habitable area is their atmospheres. But it gets more complicated than that. So let's go and visit these places and see what these atmospheres are like and how that affects the habitability of these planets. So first we're going to go to Venus. Venus is the second planet from the sun. It's pretty close, so you think it's going to be pretty hot. Let's see. Zooming in here, the blue line is the Earth. Here comes Venus. You can even see that kind of cloudy image back behind it. That's our Milky Way galaxy. Some of you might have seen that in the sky before. It's a really cool sight. You got to get somewhere really, really dark first. All right, coming up on Venus here. Beautiful. So this is Venus, kind of. You're not actually seeing the surface of the planet here. What you're seeing is its atmosphere. Venus is shrouded in a really, really thick atmosphere. It's all clouds, and those clouds are like 90% carbon dioxide. The other rest of it is clouds of sulfuric acid. Not a fun place to be. So because it's surrounded with all of this carbon dioxide, these really powerful greenhouse gas, you'd imagine that the surface of Venus is really, really hot. And you would be right. Average surface temperatures on Venus are something like 830 degrees. So very unpleasant. And all of that atmosphere pushing down on the planet also means that the pressures at the surface are about 90 times what they are here on Earth. So that's even worse than like going to the bottom of the ocean. Not good. That also makes it really hard for us to study Venus. So we've hardly been able to land on it at all. The Russians did have some luck back in the 70s. I think of the 14 landers that they tried to land on Venus, they got 2, which is pretty good. They're called the Venera landers. Venera is the Russian word for Venus. So they were able to land on the planet, take a couple of pictures and some measurements really quick, but they fried up in about an hour. So the image you see there at the bottom of the screen, those are actual pictures from the Venera landers of the surface of Venus. See, does not look too pleasant, yeah? The spiky bits are just pieces of the spacecraft, but it's just sort of rocky and dusty.
Oh, they're meant to keep the aliens away.
That's one idea. They don't want us there. Maybe they're hiding something really cool. We don't know. But we think that all of this carbon dioxide in this super thick atmosphere probably also comes from outgassing, from volcanoes. We have a lot of evidence that says that Venus is maybe still volcanically active. So this picture of Venus that you're seeing here is what it looks like when we look at it in radar. The really bright spots are areas where it's really, really hot. So you can see there looks like there's kind of little clumps there where there might be a volcano or cracks that sort of look like faults that we have here on Earth. So some people think that Venus might have some tectonic activity like we do. There could be Venus quakes going on. We really don't know. Here's a topographic map where you can see the low spots and the high spots. So we've been able to determine a few things about Venus, but not a ton. There's actually 2 missions that are trying to get approved to go and study Venus. One is a balloon that's going to descend into the atmosphere to specifically measure the atmosphere. And then another one that's going to try to land and to figure out some of the geologic processes that are happening on Venus. Is that a concept rover?
I believe so. It says the AREE rover.
AREE. I love it. He looks like he could handle some rough terrain. That's pretty cool.
Yeah.
I like it. But Venus does kind of have what we call this runaway greenhouse effect. So a lot of us look at Venus as sort of like what could go wrong. if we aren't careful with how much carbon dioxide we put into our atmosphere, this is a very real thing that could happen to us. So I don't know, Venus has definitely earned its nickname. Sometimes people call it Earth's evil twin. It's such a cool little robot. All right, so that's Venus, but let's move out to the other side and check out Mars. Mars is kind of the opposite of Venus in a lot of ways. Keep scooching out here. Ooh, here's a question from Everett. How do we know what the atmosphere is made up on Venus? A couple different ways we can tell what the atmosphere is made out of. One was those landers that Russia sent over. They went through the atmosphere and took measurements as they were going. So they could kind of sniff out whatever was in the air as they were falling through. We also use a technique called spectroscopy. It's kind of a complicated thing, but we basically shoot light at the atmosphere and see what reflects back. The light that's reflected back to us depends on what the atmosphere is made out of. Each element reflects light a different way. And so we can, if we know how an element reflects light in particular, we can look for that sort of signature. It's like a fingerprint. And we can tell that that element or that gas is present in that atmosphere. So that's how we know what lots of things are made out of. Even if we've never been there, we can look at atmospheres, the surface of planets, surface of stars. That's our main way of finding out what things are made out of, is using spectroscopy. In fact, that's one of the things that I do in my research, and it's really, really cool. So here we are at Mars. Mars is very red, it's very dry, it's very dusty. And right now, it doesn't have very much atmosphere. It's about 10% of the amount of atmosphere that we have here on Earth. But we don't think it was always that way. We have a lot of evidence that there was once liquid water flowing on Mars. We see that in some of the formations that we see on the surface. When we send our spacecraft to fly over it and take a bunch of pictures, we see things like river valleys and gullies, where you can see that there was almost certainly liquid water flowing on the surface at some point. That's not possible anymore, so we know that there had to be something going on in the atmosphere. I love these pictures. These are so great. The one in the very bottom center is my favorite. It reminds me of like my family's home in Houston, the river deltas and things. It's really cool. So yeah, so we know that there was flowing water there. Some people even think that Mars might have once had oceans and seas and continents, very much like Earth does. An excellent question I just saw pop up. That's what I was just about to get to. What is the atmosphere of Mars made out of? Guess what? It's carbon dioxide. The stuff is everywhere, but it's not very much of it. This is what we call wet Mars. This is what it might have looked like. Using topographic maps, we can kind of figure out where the low spots are. Maybe that's where the oceans were, higher spots where there's continents. There's some big volcanoes that kind of pop out every now and then. We love fun little visualizations like this. The part that gets weird is that it doesn't have that anymore. There's obviously no liquid water on the surface, none at all. It's far too cold for that. Mars's temperatures are around like -80 generally is kind of the average, and that's in Fahrenheit, so way too cold for liquid water. You might have noticed it does have a lot of ice. Mars has ice caps, just like we have here on Earth. There's a brilliant one. And just like on Earth, they're made mostly of water ice, but they also have a lot of carbon dioxide ice because that's what's in its atmosphere. And it has to be really, really cold to freeze carbon dioxide. Carbon dioxide ice is also known as dry ice. You may have heard of that before. So yeah, Mars is kind of cold and dead. It lost that atmosphere, and we're not really sure why, but we have a good idea. We think that Mars has also lost its magnetic field. Our magnetic field here on Earth protects us from a lot of solar radiation coming from the sun. And that kind of helps us keep our atmosphere in check. But if we didn't have that magnetic field, those solar particles can actually hit the atmosphere and strip bits away. Little atoms of our atmosphere can be flung out. And so that's what we think happened at Mars. It lost that magnetic field and it lost most of its atmosphere. It's still losing some atmosphere today. There's a special mission right at Mars right now called MAVEN. It's been out there since about 2015. It's all run from right here at CU. So it's a really cool mission. It's out there specifically studying Mars's atmosphere and trying to figure out where it went wrong, what happened to it, where it's gone, that kind of thing. So we see that the location from the sun has a lot to do with habitability as well as atmospheres. And that's not true just here in our solar system. This is true of pretty much any star system. And we know now that there are tons of star systems out there. Our star is not the only one with planets going around it. We have found thousands of these things called exoplanets. You might have heard that word before. These are just planets that are going around a star that isn't ours. We're going to pull out from our solar system here. It's just one of billions. Now, for a long time, there was a telescope out in space called Kepler. And Kepler's whole job was to look for these exoplanets. It would point up in the sky and point at a star and wait to see a planet. But planets are really, really small compared to their stars. And so you can't just look out and see an exoplanet. That almost never happens. I think we found like 2 using that method. What Kepler did instead was use something called the transit method. And he's basically looking for little eclipses. So he'll point at a star and wait for a planet to pass in front of it, like you see here on this GIF here. And as that planet passes in front of the star, it blocks some of the star's light. And so if we measure the brightness of the star, we'll see it make a little dip every now and then. And you can see here on the graph, little planets make smaller dips, big planets make bigger dips. And this is the prime way that we find exoplanets now. This is how we found almost all of the exoplanets that we found, is using this transit method. In fact, all the little dots that you just saw appear here, these are places where Kepler found at least one planet going around a star. Each one of those dots is a star. And that's at least one. Sometimes there are 2 or 3. There's one system that has 7. You can see that one bright patch right there. That's where Kepler's motor broke. And he just stared at the same patch of sky for a really long time. But look how many stars he found with planets going around them. There's tons of them. We're up into the tens of thousands, I believe now. We're getting a lot of these things. They're everywhere. And because stars are different sizes, their habitable zone, their Goldilocks zone around a different star is going to be different than around our star. In fact, Parker, pull up that Goldilocks zone picture again for us, because that had a really good comparison on it.
Yeah, will do.
Thank you. So you can see the bottom one is our solar system. The one on top is a system called the TRAPPIST-1 system. This is one of the solar systems that we found that has 1, 2, 3, 4, 5, 6, 7 planets going around it. How crazy is that? But its star is a lot smaller than ours. And so its habitable zone is actually farther in. You have to get closer to the star because it's not putting out as much energy. So you're not getting as much energy from the star unless you're closer to it, which is pretty cool. Unfortunately, Kepler reached the end of his life about a year ago. It was pretty sad, but we have a replacement, a brand new telescope that just went up about a year ago called TESS, the Transiting Exoplanet Survey Satellite. And TESS is up there doing the exact same thing that Kepler was, looking for transits of planets in front of stars, but TESS has much, much better technology. And she actually has the ability to detect atmospheres going around other planets, the exoplanets. We can see exoplanet atmospheres now. And we do that using the same thing I was talking about with Everett, spectroscopy. We can see the light coming from the star as it goes through the planet's atmosphere. And it'll change and reflect differently based on what chemicals are in that atmosphere. So we haven't done too many of these yet. This is a brand new thing that we've been doing, but they've already found just in December an exoplanet about 120 light years away that has water vapor in its atmosphere, and it's also in its star's habitable zone. So this is a really exciting thing that's been happening. We're finding other planets far away that could potentially even be habitable. I mean, we're a very long way from actually getting to these planets. 124 light years is a really, really long way. But we're getting there. We're getting closer. So this is a really exciting thing that we've been doing, is being able to see atmospheres on planets hundreds of light years away. This is also a really exciting thing that we're hoping to use the James Webb Telescope for as well. Once that eventually gets up in the sky, James Webb is going to have even better telescopes, and that's really going to help us pick out these tiny little atmospheres. Hey, that looks like a star.
It is. It's the TRAPPIST-1 system.
Aha.
There we go.
Brilliant.
Yeah,
so there's our TRAPPIST star there in the middle. You can see the orbits of the planets going around it. All 7 of them.
There's all the planets.
Very cool.
There we go. Now we've taken a trip to another solar system.
There you go. We have gone across to an entirely different solar system. Thanks, Parker.
Of course.
That is very cool. All right, and with that, we've got a couple of minutes left, and like I said, I did want to dedicate some time at the end for questions that people might have about atmospheres or habitable planets, planets around other stars, things like that. So if you want to drop those in the chat, Emily will pop those over to me. I see one that we had earlier from Amy. Is it hot or warm at all on Mars? Generally, no. There are some areas right along the equator which at just the right time will get above 0. But that's about as warm as it gets on Mars. And you have to have just the right conditions for that. Sometimes it has these global dust storms. It's not much of an atmosphere, but it's enough that they have dust storms that can cover the entire planet. And so that helps kind of keep in a little bit of warmth if it has sun. But yeah, look at the little dust devils. Aren't those cool? But in general, Mars is just very, very cold. Robin wants to do a TRAPPIST flyby. That was the one we just went to. The system we were looking at just a second ago, that was that TRAPPIST-1 system. 7 exoplanets. It's crazy. I love it. Anybody else?
And if we're talking about our solar system a little bit here, we can show them a little bit of why Pluto is no longer considered a planet.
That is a question that I get all the time. And I see you've got it set up nicely here.
Yep.
Yeah, one of the things that separates dwarf planets from other planets is the way that they orbit around the sun. And we're backing out here. So you can see all of our planets kind of orbit around the sun in a flat disk. But the purplish grayish line you see there is the orbit of Pluto. And you can see it's not in that same plane that we found earlier. So it's kind of cockeyed. And all of our dwarf planets kind of do this. There's 5 dwarf planets altogether, and they all have these strange kind of sideways orbits like that. So they're all kind of wonky. And that's just one of the things that separates a dwarf planet. Yeah, see, look at that. Craziness. They're all over the place. But here's one from John. How can we learn about characteristics of exoplanets? Surface temperature, composition, life. John, it is very hard. It is a tricky thing to do. We rely a lot on spectroscopy, on shooting light at it and see what reflects back at us. That is our main way of telling things like composition. It gets a little more complicated when we want to learn about surface temperature. You have to consider what that atmosphere is made out of, how close it is to the star, and how much radiation it's getting from the star. You have to look at other planets around it. Have to decide if it even has a surface. A lot of the exoplanets that we find are called hot Jupiters. They're really big gas giant planets that are really close to their star that, like Jupiter, probably don't even have a surface. We don't really know. So there's a lot of speculation involved. We're kind of doing our best guesses on a lot of it. But we get better and better technology, better and better telescopes, so we can learn a little bit more each kind of iteration. So hopefully we'll get a better grasp on these sort of things in the near future. But we're already doing pretty good. Here's one from Natalie. An exoplanet J1407b with a ring system that extends for 40 million miles. Wow. So I haven't heard of that one, but that sounds really cool. Let's see, I don't know if we have that one in our system, but I'll have Parker take a look and dig around and see if we can't find one.
Can you say the name of it one more time?
J1407b.
1407b. All right, I'll take a look.
This is how we name our exoplanets. They're actually named after their stars. Not all stars have names. Some of them just have kind of number tags to them. So exoplanets don't always have the coolest names. Neither do stars. It says ring system is 200 times larger than Saturn's, discovered in 2010. Very cool. 2012, pardon me. So yeah, ring systems are actually a pretty common thing, even in our solar system. All of the outer planets have rings. Jupiter, Saturn, Uranus, and Neptune all have rings. Saturn's are definitely by far the most spectacular, but we see these all over the place. And they can come from a lot of different things. One of the prime ways that we think that ring systems form are moons that were once orbiting around the planet and maybe got a little too close to the planet. That planet's gravity could actually pull that moon apart. In fact, this is what's happening with one of Mars's moons. It has a very small moon that's kind of on an inward spiral. It's about to get strung out into a big ring around Mars. That's a few million years from now, so we're probably not going to see it. But that's what we think happened with Saturn. These moons can also get destroyed by getting hit by other moons or really big asteroids or something slamming into it that can break it apart and form all those tiny particles. That's the cool thing about rings. They look really solid and substantial from out in space, but when you look at them up close, they're actually made of tiny, tiny, tiny particles of like ice and rock, everything from like centimeter size to the size of a Volkswagen. So they're not really solid at all, which is pretty neat. See, Robin asked, were we inside Jupiter? We totally were. That was one of my favorite things we can do. We can actually go inside Jupiter, at least here in the planetarium. In reality, you can't really go inside Jupiter, at least not very far. And Jupiter is a gas giant. It is essentially all atmosphere. As far as we know, there's probably not a solid surface inside of Jupiter. It's just atmosphere. But it is so big, and that atmosphere pushes down so hard, just like the atmosphere of Venus causes the surface pressure to be really high. The atmosphere around Jupiter and even around Saturn is putting a lot of pressure on the inside of that planet. And so we think that you get really strange things like metallic hydrogen, which we can't even create here on Earth. It's kind of a theoretical thing that we think that might be what's happening. But there's no way for us with our current technology to find out, really. We did crash one satellite into Jupiter back in the 90s, but it told us a lot on its way down, not enough to get all the way to the center, though. That pressure builds up really quickly. It gets very, very hot. And so spacecraft don't really last as long. But Jupiter's clouds are very, very interesting. Actually, I bet we've got a lot of really great pictures from Juno that we could show of Jupiter's atmosphere.
We do. Oh, geez. We gotta get out of Saturn here.
Do any of the other exoplanets have names? Question from Amy. They do, but they're not any more interesting. I don't think, there's not really any that have typical names like you would think of with our planets, named after, Greek gods or Roman gods, Mercury, Venus, things like that. They're all like WASP 12b. TRAPPIST-1a, things like that. So we name them after their star and the order in which they were discovered. So the first one that we found around TRAPPIST is TRAPPIST-1b. They start with B, not sure why. So then the second one we found was TRAPPIST-1c, and so on from there. So they do have names, they're just not always the best names. Sometimes astronomers do give planets nicknames, planets and asteroids and moons and things like that. You'll hear those from time to time, but they're not official names. So yeah, Parker's throwing up some cool Jupiter pictures. This is one of my favorites. So these are auroras on the north and south pole of Jupiter. Yeah, Jupiter has crazy auroras because Jupiter, because it's so huge, has a crazy magnetic field, and that's what causes these auroras. Now, the spacecraft Juno is super cool because it's out at Jupiter right now. It just made its 26th orbit around the planet, and it's the first spacecraft that's ever orbited Jupiter from north to south instead of around the equator. So for the last couple years, we've been getting our first looks at the north and south pole of Jupiter. We've never been able to do that before. And we found these crazy auroras. Like, look at that. Isn't that nuts? You can even see the little, it's like kind of round in the middle, but on it's my right, maybe it's your left, the little kind of tail that's poking out and swirling down. That's a trail in the magnetic field from one of Jupiter's moons, the closest moon into it, Io. It interacts with Jupiter's magnetic field and causes this little tail in the aurora. So you can kind of see a track from the moon. It's really nuts. I love it. Here, Emily says, do all planets have magnetic fields like Earth? Not all of them. There are different ways to have a magnetic field. There's a couple of different kinds. Planets that have one like Earth, those are planets you have to have a couple of things. One of those things is a molten core. So the inside of the Earth, it's magma all inside. And in the very, very center is a really thick core of iron. And some of that iron is solid, but some of it is liquid. And the kind of sloshing around of this liquid metal creates our magnetic field. And so this is an internal magnetic field. Earth has one. I think Venus, off the top of my head, I could be wrong there, but I know the Earth definitely has that. Mercury has one like ours too. Mars is a little different because Mars is small. Its interior cooled down a lot faster than ours, and so it's already solidified on the inside. And so it can't generate that magnetic field in that same way with the sloshing liquid. It does have magnetic fields from kind of induced from the solar particles that are hitting it. Those solar particles are charged, and so they can hit the surface and cause these sort of what they call crustal auroras, where the surface of the planet has different areas of magnetic charge. We see the same thing on the moon too, these weird little pockets of magnetism. It's really, really interesting. Let's see, are the rings of Saturn made of crystals? Yeah, they're like little tiny ice particles. Let's see, will the aurora wane during a superior conjunction, like a shadow effect? Ooh, interesting. So it may wane in how we see it. If the light coming from another planet, or if we're talking about auroras on other planets, then yes, if that light coming to us gets blocked, we're not going to see as much of the auroras. If you're talking about here on Earth, and if something is in between us and the sun to where those solar particles aren't hitting us as much, then yeah, they will be a little lessened. But if those solar particles can make it around whatever's in front of us, or if there's nothing in front of us, then we'll see those auroras really bright. But if anything is between us and the sun, it will block some of those particles from getting to us, and that'll cause the auroras to kind of die down a little bit. Excellent question. So yeah, the picture Parker's got up now is kind of a representation of our magnetic field. Comes out one side and around and back in the other. Of course, it's invisible. You can't actually see these lines, but that's kind of what it would look like if you could. All right, got a couple more minutes left if anybody has any other questions. You guys have had some good ones. Ah, the auroras on Jupiter. Gotcha. From here on Earth, it would be really difficult for us to see them. The spacecraft itself will probably not notice any changes as long as the same amount of solar particles are hitting. Can Earth block it for Jupiter? Possibly. It will block some of them, but Earth is really, really, really tiny compared to Jupiter, so it's not much of a block. It'd be like, if I put a pea right out here, it's not going to create too much of a shadow from the spotlight there to my face. A little one, but not very much. Jupiter, I think you can fit 30 Earths across the diameter of Jupiter. You could fit something like 1,000 of them inside. It's crazy. Jupiter is crazy, crazy huge. So the Earth isn't going to block too much because the sun is even bigger than that. So you're going to get a lot of spillover around the sides. That is a good question. I've never thought about that. That's fun. All right, seems like we're kind of winding down here, so we'll go ahead and call it a day. Thank you guys so much for coming out today and joining us for Dome to Home. Be sure to join us next week. Today is actually the 30th anniversary of the Hubble Space Telescope. So next week, we're going to be celebrating that as well. So we'll have our kindergarten through 5th grade shows Monday at 11, 6th through 12th grades Wednesday at 11, and then our normal public shows like this one will be 4 o'clock on Friday, 4 o'clock Mountain Time. So be sure to join us for some of those upcoming shows. Otherwise, thank you guys so much again for coming out, and we hope to see you soon. From me and Parker and Emily, we'll catch you next time.